Yes.
this morning.
Yes, thank you very much, Enrico. So I hope, for me, the time after the lunch is always the worst, because then all my blood is in the is here below and not here. But now, of course, because I'm a lecturer now, I won't fall asleep. But I'm not really. I hope that you don't fall asleep because. Okay, let's go. So the plan is for this lecture is the following. So I start with a short recap what we heard in Giovanni's talk or lecture about the Peccei-Quinn solution of the strong CP problem, and then I introduce benchmark models for the or benchmark UV completions of the standard model or of the Peccei-Quinn mechanism, which provide then a Peccei-Quinn solution of the strong CP problem. And one of them is the so-called KSVZ model, or types of the types of KSVZ models, for where KSVZ stands for Kim, Schiffman, Weinstein, Sakharov. And then about DFSZ models for Dine, Fischler, Srednitsky, Ziditsky models. And then I will also talk shortly about grand unified theory Axion models. So let's start with the recap of the Peccei-Quinn solution of the strong CP problem, which is nothing else than so it's based on the fact that one promotes the theta parameter of QCT to a dynamical field. And so very shortly, so one, as Giovanni has told us, one adds to the standard model a Nambu-Goldstone field. So essentially an angular field or a dynamical angular field. So scalar field divided by Fa, where Fa is the so-called decay constant, and this field should act over between minus pi and plus pi, and this field should act with the standard model exactly like a dynamical theta parameter. So we have in the standard model we have this theta term, the theta bar, times alpha s over 8 pi times the chi dual, where chi are the gluonic field strengths and dual is its Hodge dual. And then one adds to this model a dynamical Nambu-Goldstone field, theta, which has a kinetic term, and the kinetic term involves the decay constant to make it dimensionally right. And this is exactly the analog of the decay constant of the pion in the pion Lagrangian. But one adds to this a term which exactly looks like the theta term, but instead of theta bar, one has here a theta of x. So, because it's supposed to be that it's a Nambu-Goldstone field, of course, this has to be a periodic variable, and this is also in line what we said, that the space-time integral of this term is an equal integer number. Now, so as I said, in analogy to pion physics, this Fa is dubbed the Axion decay constant, and of course, because this is a dimension 5 interaction, this theory will break down at scales of the order of Fa, of order this decay constant, and therefore it needs a UV completion at scales above this scale. And and my lecture is just about possible UV completion, and I concentrate on field theoretical UV completions. There can be also stringy UV completions, but this is not the subject of my lecture. So now, if you have this, as Giovanni has also, so I just repeat now what Giovanni said. So now the theta bar parameter of QCD can be eliminated just by a shift. So I replace theta by theta minus the theta bar, and then this QCD term is erased, and I have just I'm just remaining effectively just with this interaction. So the Lagrangian will be just be given, which just look like that. And from that, so many things follow. And so it's very nice. So it's very simple. It's such a simple theory, but so many things follow from it, just by chiral perturbation theory and all these things which Giovanni was talking about. Namely, so if you have this, then the strong CP problem is so to say solved by QCD itself. And this is really a very nice thing. So the QCD itself is doing it. And how is it doing it? Because now if you integrate out the gluons, or you go to the low energies where there's low border gluon degrees of freedom by using the chiral perturbation theory, you find that this term is then effectively producing self-interaction potential for the axion, which is of this form. So it has it's a periodic function, and it has an absolute minimum. It has an absolute minimum at theta equal to 0, which means that the strong CP violation is the strong CP problem is solved by the dynamics of QCD itself, because the vacuum expectation value of this theta field, or of the axion field, is 0. So QCD solves this problem by its own dynamics. This is a very nice solution of the strong CP problem. Now, and of course, in effect, I mean, Peche and Quinn, you don't find in their original paper, you don't find this potential and so on. There were more arguments, so to say, why the theta effectively is 0 in the vacuum. But so this understanding came later. You see, this is later than Peche and Quinn was in 77, so this investigation came a few years later, but they explained, so to say, why this Peche-Quinn mechanism is working so nicely. And it was also very interesting. So I talked to Roberto, who was my boss at DESY for some time when I started as a postdoc at DESY, and he was really embarrassed that he and Helen Quinn, they didn't realize that there is a particle associated with this mechanism. Similar then that it could be that Higgs was not really emphasizing very much in the first version of his famous paper that there is a particle associated with which can be searched for. And here also, so of course now it's clear, and from the Goldstone theorem it's also clear. But so they were not thinking about that, But Weinberg and Wilczek, immediately after Peche-Quinn, their solution of the strong CP problem, they pointed out there must be a particle associated with this mechanism, and there must be a particle excitation, and this particle was then dubbed axion by Frank Wilczek, because he said, okay, this cleans up a problem associated with an axial current. And Axion is a cleaning detergent. And so he thought this is the perfect name for this particle because it solves this problem with the axial current nicely. And of course now from this expression of the potential, you can you can take the second derivative and calculate the mass of this axion. And so the maximum mass is determined by the second derivative of this potential, and it's given by this formula. So this is, of course, this is the leading order formula. And you see, as Giovanni also emphasized, the mass is, so to say, something, there's a seesaw relation between a scale of chiral symmetry breaking, m pi, f pi, and this Fa, which is essentially, which we see later, is essentially the breaking scale of a U1 symmetry, of the U1 Peccei-Quinn symmetry. Now, if you put in value numbers, then it's 6 milli-electron volt for a decay constant of 10 to the 9 GeV, or one can do it much more precisely by using NNLO corrections in chiral perturbation theory and taking into account also order alpha QED corrections to this result. So this is the nowadays best estimate or best precisest prediction for the axion mass in terms of the decay constant. Now let us, at the moment, so this was a completely phenomenological model. You just said, I put in by hand I replaced the theta parameter of QCD by a dynamical field, but how can this dynamical field arrive from a UV completion? And so one of the simplest one, so there was of course a very simple one, which was already, well, it was not so simple, but was advocated by Peccei and Quinn, but this gave rise, so they had to extend the standard model by 2 Higgs doublets. We will see this later in the context of the DFSZ model. However, it had a phenomenological problem because this decay constant was not so large, and therefore this axion was visible. So, and it could be ruled out very fastly, but you see 3 years later, Kim, Schiffman, Weinstein, Zakharov, they came up with a model which produced an invisible axion, a UV completion, which produced an invisible axion. And I will, so these models which I am talking about today, they are all belong to the class of invisible axions. They are not really invisible because otherwise we would not be so excited about the experiments which are all going on. But at the beginning, when they were proposed, it was just they were called invisible, and only later people like Sikivi and so on, they pointed out ways how to look for experimental or even experimental ways how to look for the axion and make it visible. So now this simplest model, the so-called KSVZ axion model, it's based on a minimal extension of the standard model. One adds to the standard model a singlet complex scalar field sigma, which features a spontaneously broken global U1 symmetry and a vector-like fermion in a fundamental of color and singlet under SO2 left. So this is essentially sometimes called an exotic quark, and neutral under hypercharge. So this was the simplest thing what they were proposing. So the Peccei-Quinn symmetry was realized as following. So one assumes that under U1 Peccei-Quinn, these new fields, they transform So the sigma had, so to say, a Peccei-Quinn charge equal to 1. It transfers under this U1 as e to the I alpha sigma. The left-handed part of this colored fermion had a Peccei-Quinn charge 1/2, and the right-handed of -1/2. So it was a chiral Peccei-Quinn charge assignment. And if you suppose now these transformation, then you can write down the simplest or the most general renormalizable Lagrangians for this theory, which of course consists of this kinetic term of the complex scalar field, of a potential. So we said we want to that this bond has the features of spontaneously broken U1 symmetry. So this has the typical Mexican hat, or I should not say any Mexican hat anymore. It's the bottom of the wine bottle potential, and then of course the gauge kinetic term for for this quark, where this d mu, this covariant derivative, contains the gluon fields. So we said that this Q is in a fundamental of color, and this is the most general Yukawa interaction. So this is really. Then now you can easily check. Of course, this is Peccei-Quinn invariant because it was only the modulus of the sigma field. This is, in any case, Peccei-Quinn invariant, and this mass term is also Peccei-Quinn invariant because you get from this, you get a minus 1/2 charge, plus 1/2. This left has minus 1/2 charge, and this has also minus 1/2, so in total -1, and the sigma has +1, so this is also invariant. So this is the simplest thing you can write down. Now, of course, if you now decompose the scalar field in polar coordinates, which is convenient, and you so to say you decompose it in a radial component or in a modulus component, which goes, so to say, along the direction of the modulus, but it so to say it accounts for that there is this minimum, and so to say it describes the fluctuation around the minimum in the radial direction. And there's the other field, the other component is the field which gives the angle, so to say, the angle of the field around this potential. Then we see that this model features 3 BSM or beyond the standard model particles. So, of course, it will have a Goldstone field. The Goldstone field corresponds to excitations along this along this angular direction. This will turn out to be the axion later. Then there's the excitation of the radial field. The excitation of a radial field, which will have a mass proportional to this V sigma. So this looks like the formula for the Higgs mass. Square root 2 times the quartic coupling times the vacuum expectation value. And if this vacuum expectation value is much larger than the electroweak scale, then this is a very heavy particle from our point of view, and probably not observable in the near future. And there will be this new fermion will also get a mass. The mass will also be proportional to this V sigma because it arises from this term, and will be proportional to this Peccei-Quinn breaking scale times the Yukawa coupling, and unless the Yukawa coupling is super small, this guy will also be quite heavy. So, and then, of course, so we suppose that for a large Paget-Quinn symmetry breaking scale V sigma, these latter two particles are heavy and they may be integrated out if we are only interested at the effective theory at energies much less than the breaking scale. Now, how to integrate? So now, what happens if we integrate out? So if we integrate out rho, we are left, so to say, with the gauge kinetic term of the Axion field, and still with this exotic quark kinetic term and the mass term. And of course, now this mass term has this funny factor, phase factor e to the I a v over sigma. So it's not so easy just to integrate this out. So, or how to understand what this is meaning, and therefore so in order to integrate also the heavy quark out, we should bring this term to the form of a standard mass term. And this can be, of course, done by to bring this in a standard mass term if one performs the field-dependent axial transformation, which looks like this e to the I minus I half gamma 5 a over v sigma. So that is, we transform the left-handed field, for example, by this factor, and the right-handed field by this factor, and then so then this factor is cancelled. However, and this we also Giovanni mentioned, the path integral is not invariant under this change, and so I'm also not giving the full derivation, but first I want to give a flavor, so how this can happen. So the fermionic measure in the path integral is not invariant under space-time dependent axial transformations. So in fact, so first of all, it can be more or less. Normally this is a Spinor path integral. It's always proportional to the determinant of the eigenvalues, rather than 1 over the determinant or square root of the determinant of the eigenvalues. So it's proportional to the determinant of the eigenvalues, and so more or less, so it should be proportional to the determinant of this transformation of this phase of this e to the I phase to this e to the I a of x v sigma gamma 5. Now you can also write it. So normally you can write a determinant as e to the trace, and so you can write this determinant as e to the integral d4x a of x trace of gamma 5 times a delta function. And so and this is nothing else than now this so-called Fujikawa factor, or this Fujikawa Lagrangian you get from this non-invariance of the path integral under axial transformations. Now, here is a problem now to really calculate. So Fujikawa's main contribution was really to give a gauge invariant way to calculate this expression. No, so first, because at the moment, at this part, so it's not gauge invariant, and it's also quite ill-defined. So trace of gamma 5 should be 0, and delta of 0 is infinite. So you are multiplying 0 with infinite. So somehow Fujikawa gave a way how to regularize this expression, and how to do it gauge invariantly. And so, in a sense, so this LF it's not just a A of x over V sigma times this trace gamma 5 delta, but the trace gamma 5, this part is essentially, he regulated, so to say, these infinities by a heat kernel method, so to say, and so there is a parameter lambda and also there is also something like that you also resolve the delta function of 0 by a point splitting, and he has shown then that the result of this calculation ends up in this formula, gs squared over 32 pi squared a of x. So this gives essentially gs squared over 32 pi squared chi dual. So in principle, there could be many higher order terms, but at the end, only one part of infinitely many terms remained. And this can be understood, so to say, in terms of this anomalous triangle graph, which was known before the calculations of Fujikawa. So the Arlebel-Shakif anomaly were known before, but here, so this is nothing else than another coin or another side of the coin of the triangle anomaly in gauge series. So essentially, it says, so to say, in principle, yeah, there could be much more. That in principle, this can be explained by this triangular graph. So and you can essentially count the numbers of g's, the gs squared. You can count here, and so the anomaly. So this the fermionic, that this non-invariance of the fermionic measure in the path integral is nothing else than saying that there is this anomalous violation of the chiral current in this gauge theory. Now, if we now use this fact, then we integrate, so to say, out, so to say, no, if we now use this non-invariance, then we understand that from this expression, we get the following one. So now from this chiral transformation, we find that this mass term can be brought to the standard form. And from the non-invariance of the path integral, we get this coupling of the axion to the topological charge density in QCD to chi dual. And of course, this term we can also understand because this comes just if we insert this transformation in the kinetic term. We get from the kinetic term, we get this 1/2 d mu r V sigma, this term, which we also saw it in Giovanni's talk popping up several times. So now we can safely integrate out the heavy quark. So and then we are left at scale, so to say, at scales much less than V sigma with the simplest axion theory. So in fact, so we can write now, of course, this expression now we can also write by identifying the theta as A over V sigma. We can write just like the theta term, and we see that this KSVZ axion model, this Simples axion model, has just reproduced at low energies, at energies much less than the Pecek-Wind symmetry taking scale has reduced to an effective time-dependent sigma term. And we can also identify, we see also immediately that this FA, in this case, FA can be identified with the V sigma, so with the Pecek-Wind symmetry breaking scale. So this is a very, very nice and very beautiful thing. Now, one can, of course, also generalize now this case, we said Axion model. Now, so we said, so we have started that the quark was a singlet under SO2 left and also a singlet under U1 hypercharge. Now we can just allow the coupling that this quark we allow that this, for example, now that this exotic quark is charged under the U1 electromagnetic. And then one gets now again by the same arguments, but now one has also to take into account instead of only the U1 Pecek-Wind cross SO3 anomaly, one has also taken into account the U1 cross U1 electromagnetic anomaly. Then one gets from this gyro transformation which brings the mass term into the standard form. One will get, in addition to the normal GG dual term, one gets also an FF dual term, a coupling to the electromagnetism. And we can also, from these triangle diagrams, we can easily also read off the anomaly coefficients N and E. Now here in the symbols case, we said Axion model where this quark is just in a fundamental of SO3. We get for the factor N, which counts here is the anomaly factor. It's just the Pecek-Wind charge of the left-handed minus the Pecek-Wind charge of the right-handed, and in my normalization it's 1/2. It differs by a factor 1/2 by the one in the famous article by Enrico et al. So this is 1/2 minus 1/2, so it's equal to 1. I like this more because in your case the n is not always so. 2n is always an integer, and why I should call it n if it's not an integer? So that is what. So therefore, I took this other factor, and here one can also count now. So now at these vertices, I have of course the charge, the electric charge of this Q sigma times E. So this E will be proportional to QQ squared. Again, it will be proportional to this difference in these Pecek-Wind charges, and the sex it counts. So this 6 counts essentially the number of colored particles which are going around. So in total, yeah, okay. Now. Phenomenology. So we will have in the next talks or lectures, and also in many talks, phenomenology is mainly dominated by looking into the electromagnetic coupling of the axion, and we have seen there is this factor E or N in this electromagnetic factor. So I want to go one step back. So this was just essentially the interaction of this this model above the QCD scale. Now we can go below the QCD scale using the chiral perturbation theory. And then the effective interaction of the KSVZ model of this generalized KSVZ models will look like that. So we will have a guaranteed interaction with photons, which comes from the mixing with the pions. So even if this quark is not has no electric charge, then still from the mixing of the pion we get this extra factor, which is of the order of 2 and which has been also calculated next to leading order precision by Giovanni et al. So in general, so this electromagnetic coupling will go like E over n minus this factor of around 2, and there will be a guaranteed coupling to the electric dipole, to the nucleon electric dipole moment. As Giovanni has emphasized, there is quite some uncertainty, but this is expressed also. I mean, here this is a factor. So it's a factor of unity, uncertainty of the whole result. But this this will be a guaranteed and not deniable prediction of the axion, and if at any point some particle will be discovered which has just the photon coupling, at some point one has to measure this coupling in order to really say that this is an axion. Until that is not measured, we can never say that it's an axion. It's only, or a QCD axion. It's just an axion-like particle. But if you measure this one, then so this is the defining property of the axion. So that it's a space-time dependent theta parameter. So okay. So now, of course, the couplings to the standard model. So this coupling and this EDM coupling, they are suppressed by powers of the axion decay constant. And so therefore this KSVZ axion, if Fa is much larger than V, or if this V sigma essentially is much larger than V, this is a benchmark invisible axion. And moreover, so one has also to realize here, because the axion mass is proportional to 1 over Fa, and because all these couplings are proportional to 1 over Fa, that means that these couplings are linearly dependent on the mass. The smaller the mass, the smaller the coupling. So they are, if you plot them as a function of the coupling, they are very, so they get smaller and smaller the smaller the axion mass is. And here there is no freedom, but here is the freedom in this E over n factor. So here I have written it down. So I have now written here this coupling A.
Andreas, I have a question.
Yeah.
Can you go back?
Yeah.
So for the dipole operator,
Yeah.
that is dimension 6.
Yeah.
So you have 1 over Fa.
Yeah.
But then you have another scale which is written there.
Which is written there.
Yeah.
This is the neutron scale. So essentially, this is essentially, if you write it, is something like the mu, the magnetic what is this mu n? So this scale is, so to say, there's a chalk. The scale which is there, essentially, it's the reduced quark mass times 1 over the neutron mass squared. So this is the scale. Okay. So, and therefore, I mean, you can understand. So normally you would have said this is 1 over the nucleon mass, then it would be 10 to the minus 13. something like that, if E centimeter, but you get from the reduced quark mass, so to say, the quark mass, so it's suppressed by the reduced quark, by this ratio. And this makes it still smaller. So now, so you have this dependence, so to say, on the mass. So I have essentially in the Ca gamma, which is this factor. This is the Ca gamma, and the other factors are as. So I mean, you write this one as Ga gamma. This is the one. This whole thing is alpha over 2 pi Fa is 1 over 4 times Ga gamma. So this is this, and therefore, so you see this Ga gamma is this factor, and if you plot it in a plot, Ga gamma versus Ma for n equal to 1, it's just one line, and now you can you can determine a band, you get a prediction, a band of predictions for electromagnetic coupling. So these gentlemen here, they have done it for us and have implemented some so to say some requirements, for example, that you don't run into Landau pole. I mean, you could make E larger and larger, but if E is larger and larger, you have more and more electromagnetic charged particles, and then at some point you hit the Landau pole below the Planck mass and so on. So there's it's quite a big band, but so this is so to say the this is the benchmark band for the KSVZ Axion models. Now, recently, and I will talk much more in about 2 weeks about that. Recently, one of my PhD students came to me and asked, so what if exotic quark? The exotic quarks carries a magnetic charge and not just an electric charge. So it's a monopole, yeah. And what happens then? and so on. I said, oh, this is a very interesting question. And so we looked into that. And it would be, of course, it would make the KSVZ Axion model much more, would give more flesh to the model, because in the KSVZ Axion model, one has just ad hoc introduced this exotic quark. But if this exotic quark is at the same time a monopole, or if this exotic quark has a magnetic charge, then because we all know that if there's one magnetic monopole in a theory, then just by the requirement of consistency of the theories, then this existent would explain not only the strong CP conservation, but also charge quantization. Because if you have a monopole, then the electric charge must be quantized. And then we looked into that, and so this is just now just a plausibility argument but it comes also out of real calculations, and this I want to show in 2 weeks. that this anomaly, that this coefficient, or this effective induced electromagnetic monopoles due to a loop of a magnetically charged quark will look very much similar to this expression, but the whole thing will be proportional to the alpha magnetic, because what is at this vertices is essentially the magnetic charge times the quantum of the fundamental magnetic charge value. And so you have replaced essentially this alpha by this alpha magnetic, and but this M is more or less the same as for the if you have an electric particle. And then just because of charge quantization, you get a huge enhancement factor, because alpha magnetic is of course this g squared over 4 pi, but g squared is, because of charge quantization, is pi squared over e squared. So this alpha m goes like 1 over alpha. And you get, so you get an enhancement by a factor of 10 to the 4. So monopolar axion would suddenly be would have a huge coupling. It's not super gigantic, but still, I mean, it would be in a range which could be tested by by the next generation, even by our ALPS 2 experiment at DESY, which starts running in the next few weeks. So I'm really looking forward to that. But I will talk more in 2 weeks about that. Now let's go to the DFZ. I have to drink something. I don't know who has somebody a glass, or I won't. If I die, then you know why. Yeah.
Can I have a question about the previous slide?
Yeah.
So did you think about what would be the physics in the ultraviolet responsible for these magnetic charges?
No, I just said, so we were just assuming that there is nothing you can say, that there is a fundamental, so that there are fundamental particles which have this charge. You can treat this via the so-called there are different treatments how you can do it, but you can do it with a path integral. I mean, so this is not. So there are methods how to do it. The funny thing is that in this case again you can do exact calculations for some things, and exactly this calculation you can do exactly how you can do it also in the novel theory, because it follows from so the anomaly is supposed to be one loop exact, yeah, and in a sense we have generalized the Fujikawa method for this case and have calculated this, and this is so there are no higher order corrections to that. So, but we would not know to calculate the scattering of these particles and so on. But how to integrate them out, we know. So, or we claim to know. We know how to integrate them out. So I don't know how to describe really in the ultraviolet how to describe this theory or calculate things in this theory from first principles. So I mean, this was the problem with this kind of thing. But I know how to do it. So, and I would also not know the cosmology of this model. Also, of course, we can calculate. So we know. So there can be again, there can be a monopole problem and so on. So we have to suppose that inflation erases all these guys. So this Patrick-Winn symmetry, I mean, these guys, they got also masses now from the Patrick-Winn scale. So I mean, so they are, and if the inflation scale is above, and there are no, if these are not produced in the early universe, then there is no problem. And then you can only, at the moment, but you could check to see for these things. So, but let's do it. I mean, this is not really for us, it's of course a benchmark now for ALPS 2, but not for the whole rest. So, I mean, maybe it's my hobby or something, but I want just to say, so I mean, you can fill up, as you know, there is also this Zn axion where you can fill up everything here above. So I don't really know what I could say about benchmarks. I could just say experiments should do what should not believe us, and so everything here is well motivated to look for. If you don't, so I mean this would be my opinion. So then let's go now to the DFSZ Axion model. I said so. Actually, it should not call DFSZ, but it should call ZDFS, because Sitnitsky's work was 1 year before Diane Fischler and Svetnitsky, but it was in Russian, and so so I don't know. So I mean, I don't know. You could of course say now it's just alphabetic order. So in this case, what? Yeah, okay, yeah. So here's the feed content and the Patrick-Winn charges. So in this case, you add to the, so you are doing, so to say, you are not adding any new fermions to the standard model. You're just using for the anomaly and for this chiral assignment of the charges, you just use what is there in the standard model. Don't, so and this, in this sense, it's also very economic. Of course, unfortunately, in this case, we cannot associate magnetic charges to these guys, because then we would not live. So I mean, there are no magnetic charges around us. So okay, and again, and so in this case, you just add this complex scalar field featuring this spontaneously broken U1 Patrick-Winn symmetry, but you extend the Higgs sector of the standard model to so I now concentrate on a type 2 Higgs doublet model. There also, you can also extend it by a type 4 to Higgs doublet model. Then you get the so-called DFSZ2, but this is so there you can always do variants a little bit. But the type 2 is very elegant or very nice, because you get it often also from grand unified theories, and it's in the minimal supersymmetric standard model and so on. Type 2 is more common, so to say. So here are the charge assignments in this case. So you do a chiral charge assignment to an axial or chiral charge assignment. You do it only to the right-handed up quark singlets and to the right-handed down quark singlets. Do a factor XU and an X and the Patrick-Winn carbon XT. Nothing to the leptons. To the right-handed leptons, you associate XT, and to the Higgs up and Higgs down, you do it XU and minus XT. And the sum of XU plus XT should be 2. So now, what is this funny charge assignment doing for us? So first of all, it gives, so to say, it leads to the fact, so to say, that the Yukawa interactions of this model are quite restricted. So if you have this kind of charge assignment, then the right-handed quarks, they couple only to the so-called Higgs doublet with the index U, and the right-handed D quarks couples to the Higgs doublets D. So which means essentially that after symmetry breaking, the right-handed quarks get their masses by the VEF of this HU, and the D quarks get the mass by the doublet T. And type 2 means that the leptons get also the mass by the D. The type 4 would be that the leptons get the mass by the U. So this is, yeah. Yeah.
They still suffer from the Higgs cycle problem, right?
But I mean, you have all, in any case, you have also you have always a hierarchy problem.
But it doesn't help.
It doesn't help with that, of course, but you can, so at least you have also, I mean, if you have the Pecek-Winn symmetry, you have an additional hierarchy problem, because, I mean, there is, you have another scale, even so, I mean, so it's no, there's no change, yeah, partly to that. So yeah, just to see, of course, I mean, you can now easily check that these terms are these are all the allowed terms, and just why they are allowed. Yeah, I mean, here the HU has the twiddle is, so to say, this kind of combination. So it has minus XU, and the UR had plus XU. So this cancels, and here the same goes on. And now then you can write the most general scalar field potential. So there are quite a number of terms. So there are the quadratic terms. Of course, they are. So most of these terms, they are in any case only the allowed one by gauge invariance. But I want to reach your final attention only on this non-Hermitian term, which is very essential in this model, as we will see. And this, so for example, it's easy to see that this last term is responsible for the explicit breaking of a rephrasing symmetry. So, but because all the other terms, they would be just if you invariant under these independent rotations. But this last term, this breaks this refacing symmetry to U1 hypercharge cross U1 Pecek-Winn. And we will also see that this parameter will be also essential to make all these extra Higgses which you have, to make them heavy, much heavier, so formally much heavier than the electroweak scale. So the parameters in this scalar potential, they are chosen such that it attains the minimum at this singlet webs. So for the neutral component of the Higgs, it's VU over square root of T. For HT, it's VD over square root of T, and for the expectation value of sigma, it's V sigma. Now, this model features in total 4 plus 4 equal 10 excitations. 4 is because there are 2, 4 plus 4, it's because there are 2 SO2 left doublets, which are complex, so these are complex, so they are, in total they are 4 plus 4, and then the 2 is because it's one complex scalar. And then, but they are of course not all physical after the symmetry breaking. 3 of those 10 are eaten by the W plus minus and by the Z bosons. But the remaining 7, they are left in the spectrum. So all this is normally not discussed in the context of this DFSZ model, but sometimes I think one should think about it. Because after all, we will have an FCC HH or something like that. So maybe for these extra Higgses, so it's a way to look for this guy too. So there are two. Of course, there are two charged Higgses. So now there are 5, and there are 5 neutral spin 0 particles. 3 of these 5s, there are 3 CP even scalars. One which I call small h. This should be the standard model like Higgs boson, which was discovered by the LHC. And then there's a big H, and then of course there is also the rho particle, so to say, the particle from the excitation of the modulus of this Peccei-Quinn scalar. And there are two CP-odd scalars. One is called the big A and the small a. And the small a is then our axion field. So for if V sigma is much larger than V, where V is 246 GeV, V is the square root of the sum of the squared of these two Higgs vacuum expectation values. And in my notation, I use the tangent beta is always, so my notation is now the notation normally used in the Higgs literature. It's the tangent beta is VU over VD. Now, these five heavy, five of these heavy scalars, namely the charged Higgses and the 3p and the H and rho. Five of these particles are heavy. So this I want to say that. So it's this H, the rho, the H plus minus, and the A. And it turns out that in this limit, so all these masses, so this spectrum of those is very compressed, and it's just essentially given by the mass squared is proportional to the V sigma squared up to order 1 factor from the time transit beta times this coupling lambda ud sigma, which is responsible for the breaking of this rephrasing symmetry. And this rho particle has also a huge mass times this self-coupling. So unless these self-couplings or these quartic couplings, so this is the quartic self-coupling and this is a quartic coupling among a quartic portal coupling, unless these are super small, then these particles are super heavy. Then there is a standard model like X boson, which has the mass of the order of V squared, and of course these parameters have been taken such that the mass squared will be 125 GeV squared, so to say, for this model. But there's no problem. And there's the axion, this Nambu-Goldstone boson, which is massless at the tree level. So, okay, so now, so we are now supposing again now, so all these particles are normally quite heavy, and they can be integrated out with no problem, unless as I said, unless these parameters are accidentally very small. Of course, for example, if you would like to do inflation with this model, then we would like to have this lambda sigma quite small, for example. Then we could do this a 2HD smash model or something like that. Now, so let us now go to the dynamics of this model at energies, at very low energies, much below the Peccei-Quinn and also the electroweak scale. So then, but now we have to be a bit more careful. It's not so easy to identify immediately the axion, because the axion will so in this model, as I said, there are these Goldstone bosons, which are eaten, so to say, by the Z boson, and the axion or the axion field in principle mixes with this field. So then one should treat this mixing. So in a sense, the Nambu-Goldstone field eaten by the Z boson, which I call here zeta of X. And this has associated the BEF of the the electroweak wave. And the axion field, which is called A of X, can generally be parameterized in terms of this phase direction. So for the HU, we have this factor e to the I xu over v twiddle of sigma. So this is not v sigma. So one has also to be careful at the end by the calculation. So one has to calculate, so to say, these factors by some requirements, which I will talk about very early and lately. And for the sigma, we have e to the IA over v twiddle of sigma. So requiring now an orthogonality of those of psi and A, which one needs to integrate, so to say, out the set boson, fixes then the Peccei-Quinn charges. The XU is then 2 times VD over V squared, and then in my notation, this is 2 times the cosine squared of beta, while the XD is 2 times VU divided by V squared, which is 2 times sine squared beta. So you see then XU plus XD will be in fact 2, which is required, which was required from the beginning for this Peccei-Quinn symmetry, and then the canonical normalization of the axion kinetic term fixes the effective Peccei-Quinn scale. So the V twiddle sigma will not be just the square root of V sigma, but it will be, so there is a correction factor. Because, but only if you take this into account, you get at the end really a periodic, you get really a periodic field. And so, but now, so after we have done that, we can integrate out the massive scalars and perform an axion so we can integrate out the massive scalars because now, so now they are completely decoupled from the rest. And then again, we have, in order to integrate out the fermions, we have to perform, or to get rid of these funny fermion mass terms. We have to perform an axion field-dependent Cairo transformation on the fermions, which is now dictated by a comparison of this. So we have to get. If we do this kind of transformation, then the mass terms, which you get after symmetry breaking, if you just put in these formulas in the Yukawa Lagrangian, you get these exponential function or exponential dependence on this axion field. And so if you do this, then you get via this Fujikawa method, you get just the standard mass terms plus these anomalous interactions with the gauge bosons. Now you can easily now understand. So you get here the number of generations times XU plus XD. And here you get the number of generations times 8/3 times XU plus XD. And this 1 over this twiddle FA. So now we can bring this to the previous standard form by introducing the axion decay constant, which is now in this case V twiddle divided by N. N is the number of generations times XU plus XD, which is 6 in this case. and E, as I said before, is 16 in our case. So E over N is 8 over 3, as promised by Giovanni. And the coupling to the fermions, this term arises, of course, now, again, as we also saw before for the KSVZ model, arises from these field-dependent chiral transformations via the fermion kinetic terms, and then so CAE and CAD are equal. They are proportional to sine squared beta over 3, and CAU is cosine squared beta over 3. Okay. So this is the end of the DFSZ axiom. I'm not talking about variants of the DFSZ axiom. You can think of now. Yeah. So therefore, yeah.
So I know one limit on beta is from permittivity. What's the other limit?
On what? What beta?
On beta and the hierarchy of curves. What limits the value of beta? It's not completely free.
The tangent beta. The tangent beta is not completely free because it determines the coupling of the quarks and so on, and there's a perturbative limit on this coupling. It cannot be too small because some of go like 1 over tangent beta, and it cannot be too large. So there is a range which is but this tangent beta.
Both the upper and lower limits.
There's an upper and lower limit on tangent beta.
Both from perturbativity.
Yeah, they come both from perturbativity. Yeah. Okay. So at least in this model, which you can exploit for the Pechnik wind symmetry, in this type 2 and in the type 4, and then they are the same essentially in type 2 and type 4 Higgs doublet models. Okay, so then finally I go to the gut axiom because now because I was asked to give some benchmark models. Now, we had no benchmark at all. So for this E over N, there are these kind of benchmarks which we have seen now. But there are no benchmarks on FA until now. So in the models which I have which I have presented, so one was completely agnostic to the FA or the Pechnik wind symmetry breaking scale. Now, so this can be different in grand unified theory models. So because in some cases, so at least if the original, so to say, if the fields which are originally breaking the gut symmetry at very high scales, if they carry a Pechnik wind scale, then you get normally a Pechnik wind scale which is, or an Axion decay constant, which is connected to the scale of grand unification. And therefore, you get, in this case, you get a restriction on that. And in the models which we have considered, because they always had complete generations, so to say. So typically, you got for the electromagnetic coupling, essentially the same result as for DFSZ model, namely 803. So here I've just discussed two things. So one is an SO10 cross U1 gut model, and there are many ways to break this down to low energies, and Luca has worked hard on all this, starting from the PhD and so on. And but here is one more. I would not say maybe minimal, but it looks quite. So at least from the size of the representations, it's not so minimal. But on the other hand, it does nicely the job. So you are breaking the SO10 via a 210 representation to the Partisan theory, and then you break it by a 126 B minus L and a B minus L scale to the standard model gauge group, and then with a 10, finally to the SO3 cross U1. And nicely, so if you do this, you can get nice unification of the couplings at around 10 to the 17 GeV. The nice thing about that, so this SO10 GUT with three such an SO10 GUT with 3 copies of the fermion 16 representation automatically features neutrino masses and mixing, biogenesis via leptogenesis, and if you do the Patrick-Winn extension, if you make, for example, this kind of Patrick-Winn symmetry, you just impose this very simple Patrick-Winn symmetry, which is written here on the 16, 10, 126, and 210. Then the most general Yukawas which we had here simplify. So you see there's one term is one term less, and the fermion masses and mixing, they get so all this gets much simpler, so to say, in a sense. So this is a nice additional feature of the Patrick-Winn extension. It adds the predictivity of fermion masses and mixing. It gives, of course, a solution of the strong CP problem and the dark matter candidate, the Axion, and also it gives it gives also a prediction of the Axion mass, in a sense. So because the Axion mass or the Axion decay constant,
I'm sorry,
yeah,
can you go back?
yeah.
What is this ML? The last mass, I didn't have time to. Yes.
It's the mass. It's the VEF, which was the VL. I have to.
Because I see the up, down, the right-handed mass. How is the mass of
It's
the
right and left.
No,
It has to do with the SO2 left.
It's a type 2C, so
Yeah, it's type 2C. Yeah.
it's the induced VAB of the 126.
Yeah.
It has a triplet.
Okay.
It's like the type 2C.
It's the type 2.
Yeah.
Okay, yeah. So you have a mixture of type 1 and type 2.
Yeah.
And that's why you can find the masses.
Yeah.
Thank you.
So the Axion decay constant here can be calculated. It's 1/3 the unification mass divided by the gauge coupling at unification. This can be neglecting now threshold corrections. You can calculate this quite accurately, but of course you have to take into account threshold. So if you neglect, just take this, then you would get a very sharp prediction of the Axion mass from gauge coupling unification. And then, but of course, you should take into account threshold corrections, then you get quite a range. So the range here in this case is from 0.02 nanoelectron volt to 2.2 nanoelectron volt. But at least the nice thing is, in principle, was just to say, if you now go down to very low energies, you can really determine all the couplings. Again, you get this E over N is 8 over 3. You can calculate the coupling to the proton, nucleon, and A. But the tangent beta is in this case not VU or VE, but there are the different VEFs playing a role. This electromagnetic coupling may be probed by the successor of abracadabra dark matter radio GUT. So it's in this region. So it's not completely out of the question, and gives a motivation, so to say, why to look in this range to this, and a similar. And gives also a motivation why to look with Caspar electric, because Caspar electric, which directly measures the electric dipole moment, would also be sensitive in phase 3 to this range of masses. But as I said, okay, the range of masses is still quite large, so to say. So the prediction is not so sharp. A prediction which is more sharp is in an SU5 GATT model, which was originally proposed by Luca, or I think it was by Bajc and Senjanovic, which so to say, which extended the minimal content of the SU5 GATT by a 24F in order to get by a mixture of type 1 and type 3 seesaw to get so this features a mixture of type 1 and type 3 seesaw from electroweak singlets and triplets. So it gives an answer to neutrino masses and mixing, and also it gives an answer to gauge coupling unification, because here in this case you can have because there is now this 24F. In addition, this helps, so to say, in order to unify the couplings at high energies, which was pointed out by Luca and collaborators. So I don't want to go into these details. The nice thing is that in this model there is a clean correlation between an effective electroweak triplet mass M3 in the unification scale, and for this electroweak triplet one can look at the LHC. And I don't know what the current situation with the LHC searches are. Maybe Luca knows more about that. But Luca, so we met at some, I think in Grenoble or so, we're discussing about this, and then Luca said, oh, well, I have a much better model where the Axion mass in principle could be, or where the unification scale can be predicted much, or can be constrained much better than in our SO10 cross U1 model. And then we started to work on that, and then we were imposing this Petschek wind symmetry on the model. Again, you can calculate the Axion decay constant in the model, and then from gauge coupling unification, taking into account the LHC and supercommutative constraints on this on the one hand on this triplet, and on the other hand on the proton decay. One has a much smaller range in Axion masses, where one could look for. The electromagnetic coupling coefficients are as in DFSZ, so I just copied it out of our paper. So again, you have to see the 803, and therefore, so this is a plot from this time. This plot, which compared with the prediction of abracadabra. Nowadays, abracadabra is called DM radio, or so the successor experiment. They are planning to go really down to 10 to the minus 19 over a whole range. So this model, I didn't update this plot. This model, dark matter radio, will really look deeply in this region. Yeah.
Remember the time scale of DM radio got?
Yeah.
It's really far future, right?
But not so far future than the FCCHH, I think. So I'm only talking normally about things which cannot be, which I hope I can still see in my lifetime. So I don't think it's more than 20 years. Huh?
Yeah, it's my impression that although DM radio in general is not super far, DM radio got was quite far, right?
It's far, yeah, but yeah.
Maybe 20.
I don't know. So, but yeah, but of course, yeah. Okay, no, this was it. The end. So, okay, and this is 5 minutes before the end. So,
Time for questions.
time for questions. I'm here for the next 2 weeks. Also, next week I'm
But
Not all the
we
time
will
here,
be
but
away 2
yeah.
days, but
Yeah.
we'll be around.
Yeah,
So,
Xavi? Yeah, yeah.
Thank you.
Look, Xavi? Yeah.
Yes, Robert Ziegler will give a specific talk.
I think,
during
of
the
course,
workshop on flavor
here
changing.
in our case, of course, I have always given the Pitchik-Wind number was agnostic
No,
to the.
this is okay. This should be benchmark
Yeah.
knowledge for the students. And then doing the workshop, we go in more specific directions.
Okay, I think it's interesting to mention that these are very particular type of axioms, right?
Yeah.
When the Chapin symmetry is playing blank.
Yeah, yeah. In principle, it does not have to be. Yeah, yeah.
Much more exciting terminology in principle.
Yeah, yeah, of course.
Okay, so we can thank you.
Thank you.
Okay.